Hey guys, it's Chili here. Welcome back to 3D Fundamentals Tutorial 21. Today we're looking at clipping. But before we get into that, let's take a quick look at the state of our pipeline. So the spaces that our vertices pass through, the various transformations, we go from model space to world space to homogeneous space. Then we go to NDC space and finally screen space. The journey from model to homogeneous space is done in conceptually we go from model to world and then homogeneous, but in reality we've got a single matrix that we multiply to go from model to homogeneous. From homogeneous to NDC we just divide by W, and then in screen to go to screen space we just do a little bit of flipping, a little bit of scaling, a little bit of offsetting, and that's how we get to our screen space, our pixel coordinates. Now in terms of the actual stages and components in the pipeline, we've got the vertices. They pass through the vertex shader. They go in triangle assembly. We make triangles out of them, and we also cull triangles that are facing away from the camera. Then we process those individual triangles with the geometry shader. Here we do the perspective divide and the screen transform. Then we go into triangle rasterization. We interpolate the vertices data to get individual pixels. They are filtered by the Z buffer. Pixel shader does its magic, and then we pixel that stuff onto the screen. And what we want to do is somewhere along this pipeline here, we want to insert a stage that is going to clip our triangles so that any parts of the triangles that are off the screen will not get drawn. Because of course that's a big problem with our engine right now. If the model goes off the screen, especially the top or the bottom, it's just going to crash the program. That's not usually what you want. Now there's one small detail that I kind of forgot in previous videos, but it's pretty important. We do our back face culling in this stage here. So we cull triangles that are facing away from the camera, and then we process them with the geometry shader. But the geometry shader could move the triangles. They could make them so that triangles that were facing away are now facing towards the camera. So what we really should be doing is we should be doing our back face culling after the geometry shader. But we didn't do it. It's not a big deal. We're not even using the geometry shader right now. But it's just something I wanted to add as a side note. Now, we need a way of preventing our system from drawing pixels that would appear off the screen. And we call this clipping. You should be familiar with this term if you've gone through the intermediate tutorials. We did a whole thing on clipping for sprites. Now there's two ways you can do clipping. You do geometric clipping and you can do raster clipping. Now raster clipping is basically what I showed you for sprites. And the same can apply to triangles. With a triangle, we've got two main loops. We're looping through Y, and then for every scan line on Y, we loop through X. So we're going to loop through X from here to here, and in this scan line, we're going to loop from X to here. So it is a loop of loops, nested loop. So to rasterize this triangle, let's say we'd have to loop from -80 to 400. Well, to clip that, you would just adjust your loop extents so that Y was never less than 0. You would start from Y equals 0, and you would end Y is never greater than the bottom of the screen dimension. So you would clamp your start and your end for X and Y to your screen dimensions, and then you would be clipping to the screen and you would not be drawing off the screen. That's raster clipping. Now in geometric clipping, what you do is you adjust the geometry itself. So what you do is you would test your vertices, you would see which ones are outside of the screen, and the ones that are outside, you would adjust them to the boundary of the screen, and then you would have a new triangle that was completely on the screen, and you could just draw it as is without any sort of clipping. Alright, now raster clipping is easy peasy, so let's talk about geometric clipping. Now the basic idea is, like I said, we want to adjust the vertices of our triangles so that when we rasterize them, none of their pixels will fall outside the screen. Now we know that any points that lie within this half cube in NDC space, if all the points of the triangles lie within this half cube, that means that when we rasterize them, all the pixels will be on the screen. In mathematical terms, that means that absolute X and Y are going to be less than 1, and Z is going to be between 0 and 1. And the way we do this is we test all 3 vertices of our triangle against 6 planes of this half cube. So let's call this the negative X plane, okay? And we're going to test our triangle against the negative X plane. Well, what we do is we test the x of each of these vertices and see if it is greater or less than negative x. So if it's less than negative x, that means it's outside of the cube, obviously. Now, if all three vertices of a triangle are on the wrong side of a plane, we know that that triangle is completely off the screen and we can just cull it. We can discard it immediately and go on to the next one. But if we have a situation where some of the vertices are on the right side and some of them are on the wrong side, then we have to adjust the vertices on the wrong side so that they are on the clipping plane. And then we will get a new triangle that has been clipped to that plane. And we do that process for all the planes, and then we're done. All right, let's take a look at how we would clip an actual triangle. We're going to clip this triangle to the near plane. So how do we do that? Well, we examine all three vertices. We see which ones are on the wrong side. We see that these two are on the wrong side. So they need to be adjusted to be exactly on the near plane, which means they need to be adjusted so that z equals 0. So how do we do that? Well, we interpolate between this one and this one to find this one. And the way we do that, well, we need an alpha for interpolation, right? So that alpha is just going to be the distance that we move. So this distance in z distance divided by the z distance between the two that we're interpolating between. So we divide this by this, we use that as our alpha, and then we interpolate from this one to this one using that alpha. And the same idea for this one here. And one thing to note here is when you interpolate, you're not just interpolating position, you're interpolating all the attributes in the vertex. So you want to interpolate, obviously, texture coordinate and normal, all that stuff. So that's the case if two vertices need to be adjusted. But what if only one vertex is outside the plane? How does that happen? Well, we need to adjust it on both of these edges here. So we need to adjust here and here. And then we'll get this. Now you notice in this situation here, we've actually increased the number of vertices to 4. So now we're not a triangle anymore, but our pipeline only works on triangles. So what you've got to do is you've actually got to split this up. You've got to tessellate this quad into 2 triangles. So if you have only one vertex that's on the wrong side, you have to clip, you actually increase your geometry, you multiply your geometry. And in situations, this can actually cause your triangles to grow, the number of triangles to grow geometrically. So let's say we're going to clip to the near plane. That gives us this guy and this guy. And then we are going to tessellate that triangle. So now we have 2 triangles here. We've got to clip both of these triangles to the other planes. So now we clip this triangle to the left plane, and we get 2 more triangles. And then we clip this triangle here to the left plane, and we get 2 more triangles. So the idea is the near plane, you put 1 triangle in, you're going to get 2 triangles out, and for each of those triangles, you're going to call clipping on the left plane, and that is going to generate 2 more triangles and 2 more triangles. So in the worst case, you could have a lot of triangles being generated from one single input triangle. And you might look at this and say, well, damn, Chili, this geometric clipping looks like a big pain in the butt. Why don't we just use raster clipping for everything? And the answer is because we can't. So when we rasterize a triangle, right, we have loops that go in the Y, loops that go in the X, but we don't have any loops or anything in the Z because there is no Z on a raster, only X and Y. There's a Z buffer, but that's a little different, isn't it? So the problem is, now let's say we're drawing a triangle, and so here's our near plane. And we're drawing a triangle. 2 of the vertices are inside of the frustum, but one of the vertices is right at the origin. So it's at Z equals 0. What is going to happen? Well, when you do your transform on this vertex, when you do your projection transform, you're going to get X is equal to 0, Y is equal to 0. Z is on the wrong side of the near plane, so it's going to be, negative, I don't know, some value, we'll say negative beta. But W is going to be equal to 0, right? Because W is just captured from Z. And then when you do your perspective divide, you're going to divide by 0, and your pipeline is going to shit the bed. So it's obviously very bad to have vertices that can possibly have a W of 0, which is why you want to clip to the near plane. But you can't clip to the near plane in raster because you only loop in X and Y. Another problem would be you've got vertexes that are behind the camera, and so they're going to have a negative W, and when you divide by that, it's going to flip it on the other side on the screen. It's going to be weird. You don't want to draw things that are closer than the near plane, so you've got to clip to the near plane, but the only way to do that is with geometric clipping. By the way, the same problem exists for the far plane as well. You can only clip far plane geometrically. However, if you fail to clip triangles on the far plane, there's no real big consequences. The main issue will be now your Z is going to be from 0 to 1 plus a little bit. So your Z won't be constrained from 0 to 1. You'll have some Zs that are beyond 1 because you didn't clip those vertices to the far plane. And because you're not clipping to the far plane, that means your draw distance will be unrestricted. So potentially you'll be drawing a lot of geometry, which might slow you down. But if you cull, because culling is easy, right? If you cull to the far plane, you probably won't have that problem. So clipping to the far plane, unless you have some restriction where you need Z to be between 0 and 1, it's optional. Clipping to the far plane. Clipping to the near plane is essential. And for the left, the right, the top, the bottom, the X and the Y, we can just use raster clipping because it's easier. So now we only do clipping on the near plane, so we don't have that problem where we multiply geometry. Now, there's a little optimization we can make here. So let's say we're clipping to the X. We're clipping to the left and the right. The expression for that would be absolute value of X less than 1. If that's true, not being clipped. If it's false, we got to clip that guy. Less than or equal to 1. Now, we could rewrite that as X homogeneous divided by W homogeneous is less than or equal to 1. Because X in the NDC space is just the X in the homogeneous space divided by W. And then if we multiply both sides by W, we get this expression here, X homo less than or equal to W homo, absolute value, of course. So what this means is that instead of first doing our perspective divide and then performing clipping, we can clip before the perspective divide. And this is actually huge because a lot of times when you clip a vertex, if you clip a triangle and all the vertices are outside, you cull that. You get rid of it. So if you cull before you do your perspective divide, you can reduce the amount of divisions you have to do. And division is a very slow operation. So we're going to perform our clipping in homogeneous space, which is also more commonly referred to as clip space. Those names are interchangeable, but people more often use the name clip space. And obviously you understand the reason, because that's where you do the clipping. Clip before your perspective divide. So here is our final pipeline. So I've added in here a clipper unit. What's going to do is you give it a single triangle input, and it will output 0 or more triangles that have been clipped to the near plane that have been culled to all the planes. And then the triangle rasterizer is going to do a little bit of extra work. It is going to clamp its loops to the raster dimensions so that no pixels get drawn off the screen in the X or the Y. So final recap before we get to the code. For each triangle, we cull against all 6 planes, then we clip geometrically to the near plane. When we're doing our rasterizer, we clip to X and Y, meaning we clamp, and we're not going to do any far clipping, but we will be doing far culling. So some triangles will have a vertex or 2 that's sticking a little out past the far plane, but it shouldn't cause us any problems. All right, now let's take a look at pipeline.h. This is basically completely a pipeline issue. It doesn't affect our shaders in any way or form, but we're going to have some major changes in the pipeline. So before process triangle, it would invoke the geometry shader, and it would pass that result on to the post-process triangle vertices function. But now we're going to insert a stage between there where we clip cull the triangle. So first thing we do is we cull. We test all the vertices of the triangle against all 6 planes of the NDC space using the comparison with W. So we check to see if X is greater than W, or if X is less than negative W. Do the same for Y. For Z, it's comparing against 0 and W. right? Because Z is only half the space. And if any of these tests fail, if all three vertices are on the wrong side of the plane, we return immediately. We discard that triangle. We don't go any further in the pipeline. But if it passes all these tests, then that means that at least part of the triangle is going to be on the screen, probably. So then what we've got to do is we've got to clip against the planes. So I've created two routines here, clip 1 and clip 2. So clip 1 is if only one vertex is on the wrong side of the plane. So in this case, V0 is assumed to be on the wrong side of the plane. V1 and V2 are on the right side. Clip 2 means that V0 and V1 are both on the wrong side. V2 is on the right side of the plane. And so you've got a little bit of different situation here. You've got to calculate alpha for both the edges, and then you've got to interpolate. So if you have one vertex on the outside, you are going to create two new vertices. We'll call them V0A and V0B. And they're going to be interpolated from V0 to V1 and from V0 to V2 using our two alpha values that we calculated here. And again, it's like I showed you in the diagram. It's just the distance that you're going to move to the clipping plane divided by the distance between your interpolated vertices in the Z, only looking at the Z here. And since we already have a nice interpolate function, this is very simple to write. And then once you have clipped, you're going to have two new triangles for the case of one vertex outside of the plane. So you got two new triangles, so you've got to call post-process twice on each of these triangles. In the case of clip 2, two vertices on the outside, you just adjust those two vertices. The number of triangles remains 1, so you just call post-process triangle vertices once. Now, the only geometric clipping that we're going to be doing is against the near plane. So I just did a big tree of if statements. First, we check to see if vertex 0 is on the wrong side of Z, on the wrong side of the near plane. And if so, we check if V1 is on the wrong side. And if V0 and V1 are both on the wrong side, we know that we're clipping 2 because our cull test has already established that at least one vertex is on the right side. So if V0 and V1 are on the wrong side, we clip 2 with V0 and V1. Otherwise, if V0 and V2 are on the wrong side, we clip 2 with V0, V2. And if only V0 is on the wrong side, we clip 1 with V0. V1 and V2 are on the right side here. And it's the same logic for, so if V0 is not on the wrong side, we check to see if V1 is on the wrong side, and then we check to see if V2 is also on the wrong side, and again. So it's just a tree of if statements, just a basic logic here. And we call clip 1 or clip 2 if necessary, and if none of them, if they're all on the right side, then we just call post-process triangle vertices. We don't need to do any clipping at all. And then the rest is just the same. Until we get to the rasterization, until we get to the actual triangle drawing routine, draw flat triangle. And it's very simple here. When we're calculating the start and the end scan lines, we just add an extra std max and std min here. So we make sure to clamp the start to never being less than 0, and we clamp the end to being never greater than the bottom of the screen, which is screen height -1. And it's the same deal for when we do the X start and the X end. We clamp that stuff to 0 and the right-hand side of the screen. And that's all you need. Now we've got our raster clipping in X and Y, and we've got our near plane geometric clipping, and we're all good to go. Now for our specular Phong point scene, I've adjusted the near and the far plane a little bit, and I've added an additional rotation in here that's controlled with N and M. So let's see what our clipping has wrought for us. So if we zoom in a little bit, we can see, oh, we're going off the bottom of the screen, but we're not crashing. So that's good. Now let's try zooming in a little bit more. And oh, can you see this? We're now clipping to the near plane on our triangle here. Seems pretty good. No crashing, no dividing by 0. Let's try this out with our, what's this dude's name again? Girl? I forget your name. Anyways, use a good girl. Let's see what happens when we zoom you in. Oh my God. Look at her butt. All right. So yeah, near plane clipping, geometric clipping works like a charm. You can see it there. It looks pretty sweet too. And of course, we're going off the side of the screen here. We're not coming out of the side here. We're going off top and the bottom. We're not crashing. It's all good. And if we go fairly far away, we can see that we're disappearing out of the back. Like that. So this isn't clipping pixel perfect. This is clipping only on the triangle level, culling on the triangle level. But it still works fine. And even though if we're doing this, that means that some triangles, some Z values are going to be greater than 1, but it doesn't really affect our program in any negative way. So it's okay. And it saves us the extra effort of also geometric clipping on the far plane. But there you have it. There's clipping in all its glory. And this is now going to enable us to have a full scene and to have a camera that moves around in the scene. So that's basically the topic of next video. We're going to implement camera transform that'll allow us to move around in a scene. I'm also going to create a simple demonstration scene for that to demonstrate various effects working together with a camera going through the scene. And that is actually going to be the final video in 3D Fundamentals before we start Hardware 3D. So, yeah, good times. We're almost there, mates. But until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D Fundamentals.